So this is part 2. There are 2 rules. They're called Kirchhoff's laws. Let's go through them right now. One is junction rule. The sum of currents entering a junction must equal the sum of currents leaving a junction. And I'll just say must be equal before and after a junction. A junction is like right here and right here, wherever there's a branch. So all the way along here, there's no branch. Every truck has to go through here, right? But what happens to it when I get to this spot? They have to choose. Either some are going to go that way or some are going to go this way. Maybe. Or something's coming this way and going up. So it might be going this way or it might be going that way. We don't know. But something has to happen where the 2 currents have to add to 1. Because it's splitting, the trail's splitting from 1 into 2. So there has to be some sort of addition there. The second rule is called loop law. I don't know why, but I always have to write it in cursive. Loop law says that in any loop of a circuit, the voltage gains and voltage drops. Bless you. Must be equal. And so another way to say that is the sum of all voltages must be 0. So sum of all voltages 0. This is an interesting thing because it's not like super intuitive. How many loops are there in this circuit? There's actually 3, right? Chris is right, there's 3. There's a loop here, the top loop, and then there's the bottom loop. And you can do the outside as well, if you want to. In order to solve this problem, we can use junction law and loop law. We don't know what's happening in this circuit. We can't work it out super easily. So one thing to do is just decide. And it'll work itself out in the end regardless of what you decide. You have to decide whether the current through this middle resistor is going to the right or to the left. We don't know. Let's just say, because 9 volts is bigger, let's say it wins. And so let's say our first loop is going this way. Okay? So let's say that our current through our 15 ohm resistor is going that way. Okay? Does that make sense? So in this loop, it's going counterclockwise. It's going the 9 volts charging us up, and it's going around like this. Okay. Once I say that, we have to assume that this loop is not going counterclockwise. It has to be going. It has to flow through the 15 this way, which would mean that in this loop, it has to be going like that, and this is my second loop. Okay. Now that tells me that actually, even though the 6 volt is pushing to the right, we're saying no, it's coming backwards through the cell.
So it's going both ways. This is just
Yeah.
antithetical. Right?
So it'd be like, you know, if Matthew Teal and I had a pushing contest. I would be pushing forward, but I probably would be going. No, he's not that. You got him? You can take him? Okay, if Radine and I had a pushing contest, Radine would beat me, and I would be pushing this way, but I would still be getting pulled back. That's not gonna happen.
No, it won't.
So we're gonna say the current through the 6 volt is actually going backwards through the cell. It's fighting to push forward, but the current is going backward. Okay. And we're gonna use one of these junctions now. Let's use this junction here. Based on our, and let's label our currents so that we can be a little bit organized, okay? Let's say that this is I1, and based on our loop, it's going to the left. And let's say this is I2, and it's going, yeah, I'm using Christmas colors, I didn't even know. And it's going to the right. And we'll say I3 through this 6 volt is going that way. Okay? Now we've just decided we're not totally sure if we're right. But we can go based on these directions. Okay. Now we gotta do some math. So we're going to say, based on our junction law, so the junction rule would say that right here well, you tell me, this is I1, right? Where's it going to go? It's going to come down and go this way into I2. And what's I3 going to do? It's going to go up and then this way. This is I2, right? Not based on what we've said for us. It might actually do that. And if you're wondering, well, what if we get it wrong? It's okay, because then the answer we get will be negative. And if the answer is negative, we know we were wrong in the direction. And your physics teacher might have set it up that way so we get a negative answer. We'll see. So how would you say this? I1, I2, I3. How would you say that?
I3 equals I2.
Good. We're going to say I1 plus I3 equals I2. So we've got an equation. This is good. Now we're going to do our loop law. Look at loop 1. Start at the cell maybe. We have a plus 9 volt, right? And then we come around this loop and we go to I2. How would we figure out the voltage at this resistor if we knew I2?
15 times I2.
Good, Nathan. So it's 15 times I2, that's going to be our voltage. And this is going to be a voltage drop. So we say negative 15 I2. Can they see this on the video?
Yeah. Yes.
Okay. Okay, what's the last bit?
Minus 22 I1.
Very good. Is that Barrett?
Yeah.
Minus 15 I...
No, 22.
Oh, sorry, yeah, minus 22. Minus 22 I1. And that's all equal to what?
Equals 0.
Good. So this is our voltage gain at the cell. These are our 2 voltage drops at the resistors. They should equal 0 at the end.
This is only for the first loop.
This is only for the first loop. So this is number 1, and it's that way. Now let's do number 2.
So it's 6.
Okay, not good. Now, look at the cell. Our loop, we said, is going this way, right?
Yeah.
So is this going to be,
Negative 6.
yeah, it's, even though this is a voltage gain, it's in the opposite direction of our loop that we drew.
Wait, what determines the direction of the loop?
We
You
decide.
do. You determine the direction of the
Says
loop.
that two's the other way.
We just said if it goes this way, this is how it's gonna be.
So if we call it going like this, positive, we have to call the opposite way.
That's exactly right.
So, but aren't they technically moving
So
at the same
this
direction?
is -6, not because it's a voltage drop. It's not a voltage drop. It's a voltage gain, but we're saying it's in the opposite direction of our loop. So we have to say this is negative. Okay, and then it goes around here,
Minus 15.
minus 15 I2, right? And that should be 0. There's no other resistor in this loop. Okay, given those three equations, math people, can you figure it out? No, you don't. What can you solve with this? I2. And if you put I2 in there, you can solve for it. I1, and if you know I1 and I2, so do it. Take a minute and do it.
Oh, 16 over minus. So wait, if your I2 is negative, then you goes the wrong way.
So I'm going to say,
Yeah, I got it. My I2 is negative.
I2 is not negative. Oh, it is negative.
You just make it positive now?
Yeah. No, you have to keep it. So this is going to be -6 over 15, right?
Yep.
Because you add the 6 over, and then you have, what is that, negative 0.4 or something, is it?
0.4.
0.4 exactly? Okay. Whoa.
Then I1's -9 minus 6 over 9.
I1?
Yeah. I1 is positive. It's 9 plus 6 over 22. Plus, you don't even need to calculate I2. You can just open I1 is moving to the right. I2 is moving to the left.
Oh yeah. So I'm overhearing some mathy people. If you want, you can just subtract these equations, right? Like you can just say this is plus 0 I1 equals 0, and you can just do this. And if you wanted to, you could, because that's going to get rid of your I2, so if you want to get I1, you can just take this whole thing and subtract it as well. And that will get rid of your I2 and give you I1. But you don't have to do that. So what was I1?
15 over 22.
Positive?
Yes.
So that's like 0.7? Like 6 repeating maybe?
It's 0.68.
0.68.
681.
We'll go with 0.68. And so then what is I3? If you add those together, oh no, you're gonna have to subtract this. So I do subtract that, so this is gonna be negative, is it positive?
No, it's negative.
It's I2 minus I1.
Negative
so it's this
119 over 110.
I mean, that's what you want.
No, it's like, it's 1.08, right?
Yeah. Negative 1.0.
Okay. So these are our totals for our currents.
Oh, you're right.
So let me just put that back on again.
Everything's just flipped. I1 is moving to the right, I2 is moving to the left, and I3 is moving to the right.
Yeah, so I did this on purpose because I wanted you to see that actually, and you could have worked this out conceptually. Actually, the 6 volt is gonna win, right? It's a lower voltage, so why does it win? Alex?
Because the current is bigger.
Sorry, say that again. Look at the resistance
Because
that
there's
the
2
6
resistors
volt.
on the top.
Yeah, the 6 volt only has to go through one resistor, right? And it's 15. But if you look at this loop, that would be 37, right? That's a lot of resistance to go through. So the 6 volt actually wins. So your current, because this I3 came up as negative, it's actually not going the way we thought. It's actually going forward. So the 6 volt is powering this. The I2 is also negative, wasn't it? Okay, so it's actually not going the way we thought. It's actually going to the left. And so the 6 volt's going around this loop. What does that mean for the 9?
It's moving to the right.
It's actually losing, right?
The 9 goes the same way.
This is positive, isn't it?
No, I1 moves to the right.
Oh yeah. Okay, and so what's actually happening with the 9 volt?
It is. I1 is to the right.
It makes a lot of sense once you see it.
3 volts.
We'll get rid of this part because it's confusing. Where this moves out of the 9 volt forward, where does it go?
It goes straight
Yeah,
down.
it just keeps going around the outside, right? Which makes total sense if you think about it. They're both pushing in that outside loop, they're both pushing in the same direction, right? So it's just going around the outside, and this happens to take some of that and go to the left.
Does any of it go through the middle?
So it's actually coming like this, and this is like that. Yes, it does go through the middle, but it goes to the left.
I3.
But the I1 never
So
goes
now we
to
need
the
to
middle.
recalculate everything.
Nope. No, you don't need to recalculate everything. It's the exact same numbers,
Okay, just.
but because it was negative that we found, it just means it's actually moving in the opposite direction.
So there is no loop 1.
There is a loop 1, but it's
It's the big one.
it would have a negative value here, right? So it doesn't actually move in this loop. It's actually moving around the outside.
So would there only be 2 loops in this case now? One big one and then one
No,
small
there's
one?
3. It's just that this value in the top loop is negative.
There isn't.
You can always calculate it, right?
But it doesn't stay there like realistically.
Realistically, there's nothing moving just in this loop. Right? It's actually moving around the outside, and it's also moving in this loop. If you see that right away, then you can say, okay, my loop 1 is the big one, and my loop 2 is this one. And then you can solve it for there, and everything will come out positive. But if you're not sure, just make it up, and then solve for it. If it's negative, you were wrong, then that's fine. Right? You just turn your numbers to positive. Nathan.
Do you consider the direction of the electrons, or the direction of the current itself?
I'm glad you asked that. These directions are not the directions of the electrons. They are the direction of current, which is opposite the direction of electron movement. When you're thinking circuits, you have to, it's easiest to just remember that they're opposite. Okay? And it's weird because they'll give you a current and they will ask for how many electrons are flowing through the wire. And you have to calculate the number of electrons, but you know that the electrons are actually moving the opposite direction of current.
Oh, so it'll just be right.
How much time do we have?
And then it's 10 minutes, isn't it?
No,
11. You can like use the last 5 minutes to go over it, Marcus.
Sorry, you don't want to do this, but I'm gonna do it anyways. Because
Can we like redo it and then
yeah, but I would rather throw this at you now rather than have to So all those circuits that we were doing are direct current circuits. They're just current moving in one direction. Everything in the house and what you plug into is AC current. It's going forward and pulling back. I'll show you how that works when we do electromag and why that is, but it's just so that you know the current is going forward and then it's turning around and going backward. Radine, what's your question?
I just couldn't hear you.
Okay. So this is voltage over time and this is AC current. This is VRMS. This is root mean square. Yeah, if you ask an engineer, what is the voltage in these wires that are powering our lights? The engineer will say 0. There's no voltage in here because it's going forward and then it's going backwards and it adds to 0. And that became very frustrating for people who are trying to build city power grids when the engineers kept telling them the voltage was 0. And they're like, how do we build this, you know? So we needed a number, and the number is somewhere about here. This is the VRMS. It's like an average. But of course, if you average all these, you're gonna get 0, right? So it's root mean square, which means you take the average and then you square it because you don't want negative values in there. So you square everything, and then you take the mean, and then you root it, right? This value is kind of like if you just had the upper bump and you took the average of that, that's your VRMS. Now you tell me, what's the average of a sine curve just for the first 180 degrees, just for pi? What angle is between 0 and 90? 45. What's the relationship of a 45-degree triangle? Edward?
Root 2 over 2.
Root 2 over 2. 1 over root 2. Right? 1 over root 2 is equal to root 2 over 2, which is equal to 0.707. Everyone say 0.707. What voltage is in these lines? About 120. That is being times by this number. So the peak voltage in your house is not 120. It's a little higher. Yeah, if you divide it by 0.707, you'll get the peak voltage. So the peak voltage times 0.707 will equal the VRMS, and that's the voltage we talk about with AC current. I got a puzzle for you. You can look it up, but try to think about it first. There's a little doodad. A doodad. It's called a diode. Everyone say diode. A diode allows electricity to only flow in one direction. We'll talk a little bit about how it works and what's inside of it when we do quantum. All you have to know right now, it's a one-way street. Electricity can only go through this forwards. It cannot go backwards. If you were tasked with the problem of charging an iPhone battery, which needs direct current, by plugging it into an outlet that supplies alternating current, how would you use this to charge the battery? Just put it there. Okay, so what Edward said is a half-bridge rectifier. If you just put in the diode, it can only flow in one direction.
But then you don't get power the other half of the time.
Oh, so
That's right.
you make a second
Yes,
wire
and then
that's
you, like,
going
make it
the
slice.
other
So you
way.
go from that, if you just put in the diode, you go like this, you get nothing, and the diode gets really hot. And then you get another one, and you get nothing, and it's very inefficient. But that is a half-bridge rectifier. So the trouble is, how do we get this guy flowing It's called a full bridge rectifier, and you can look it up, but I encourage you to try to solve it yourself. You only need 4. You need 4 diodes, and then you can do it. It's a little puzzle. Think about it. You've done extremely well today. I've given you a whole bunch of stuff. I'm going to shut off the video now, and if you want to talk to me about marks, you may do so now.